Okay, so let's talk about the next gas law now. We're going to talk about the Gay-Lussac Law, and it relates temperature and pressure. Marker here. It relates temperature and pressure. Is this working? Yep. Okay. So the learning goal is to use the temperature pressure relationship. Learning goal is to use the temperature pressure relationship. What's going on there? Why is that not going? Temperature pressure relationship. Let's try yellow, see if that works. Okay, pink. Okay. The temperature pressure relationship to calculate the unknown temperature of a pressure or pressure when the volume and amount of gas do not change. Right? All right. Kind of a mouthful there. Let's look at it. So the Gay-Lussac law is kind of like Charles' law, and it is the ratio, right? The ratio of pressure and temperature doesn't change. It's constant when the volume and amount of gas are constant also. For example, if you keep the volume constant, so here we got a piston in, let's say we lock it. If we lock that piston, the pressure might be, say, 1 atmosphere at 200 Kelvin. If we heat it up and the volume stays the same, the pressure gets greater and it goes to 2 atmospheres. All right, so let's do a sample problem and then I'll give you a chance to do your own. So gas has a pressure of blank at 18 degrees Celsius. All right, so the pressure 1, let me get a bigger marker here. Pressure 1 over T1 is equal to P2. Handwriting not very good today. P2 over T2. And pressure 1 is equal to 2 atmospheres. T1 is equal to 18 plus 273, because we want this in kelvins, right? It won't work if it's not in kelvins. And 18 plus 273 is what? 291. Okay. And T2 is equal to 62 plus 273 is equal to that. I can't do in my head. I ought to be able to, I guess. 333, 335. Just a second here. 335 on 62 plus 273 is equal to 335. That's right, 335. 335. Okay, so we're going to take this equation. We're looking really for P2. Okay, so we're going to take this equation. We're going to rearrange it. And we're going to say P2. What is going on with my markers? P2 is equal to P1 over T1 times T2, which is equal to 2 atmospheres, right? Times T2, which is 335, right? Over T1, which is 291. All right, so that gives 2 times 335 divided by 291 gives 2.3 atmospheres. 2.3 atmospheres, okay? And that's how we do that, right? So we just take this equation. I think the hard part for most students is really just this, right? Interpreting what the question actually says. All right, so let's do a learning check now. I encourage you to look at this problem. A gas has a pressure 645 torr at 128. I encourage you to pause the video, do as much work on this as you can, and then come back and compare your answer to mine. All right, so I'm going to suppose that you paused it. Let's do this here. P1 is equal to 645 torr. T1 is equal to 128 plus 273, because we got to do this in kelvins, right? 128 plus 273 is equal to 401. 401. What is the temperature in Celsius? Okay, so I'm going to have to come back to Celsius in the end. What is the temperature in Celsius if the pressure increases to 824? All right, sorry, I got a marker. I can do this right. 824 torr. 824 torr. And so we know that P1 over T1 is equal to P2 over T2. All right, so I'm just going to flip this. T1 over P1 is equal to T2 over, see, I just flipped both sides. And now I know that T2 is equal to T1 over P1 times P2. And I'll have to convert it to Celsius in the end. We'll subtract 273 from it. So T1 is 401 times P2, which is 824, divided by P1, which is 645. Okay, and I get 512.285. And I'll subtract 273 from that. That's kelvins. Minus 273. And I get 239. 239 degrees Celsius. And that is my final temperature. Okay? All right. Let's talk a little more about this now. Vapor pressure now is the pressure. Let's look at this. When liquid molecules have sufficient energy to break away from the surface of a liquid, they become vapor, right? That's vaporization. In an open container, all the liquid will eventually evaporate because it's because there are little molecules that are going to there's a statistical probability that they will be able to escape, and they'll eventually get that. In a closed container, the vapor accumulates and creates pressure called vapor pressure. Okay? A liquid exerts its own vapor pressure at a given temperature. Any liquid has a vapor pressure at a given temperature. It boils when the vapor pressure becomes equal to the external pressure. That's what boiling point is, okay? So at high altitudes, atmospheric pressure is lower than 1 atmosphere, as we saw in a previous conversation. And at low altitudes, it's higher, right? So if at high altitudes the atmospheric pressure is lower than 1 atm, the boiling point of water is going to be lower also, right? At lower than 100 degrees, because the vapor pressure of water will reach the external pressure faster, right? In a closed container such as a pressure cooker, a pressure greater than 1 atmosphere is obtained, and water boils at a higher temperature than 100 degrees Celsius, okay? So if we have the pressure at sea level, pressure 760 torr, right, or 760 millimeters of mercury. So the boiling point of water at sea level is 100. Okay, if we go just a little bit less, like we saw in some previous slides, there's some places in the world that are slightly below sea level, and then we would find that water boils at a lower temperature there, right? But if you go up, which of course there's a lot of places that have a much higher altitude than sea level, the vapor pressure is going to go up, or the boiling point is going to go up, right? So look at this. If you have a pressure cooker, let's say you have a pressure cooker and you can make this really high pressure inside your pressure cooker, the boiling point of water goes up to 180. So it doesn't boil, which is really nice, right? That means you can heat your food up really high without losing the water, and that's how pressure cookers work. Okay, so vapor pressure and boiling point was sort of just a follow-up on we were saying earlier. If you have 100 degrees here, right, and it's 100 degrees Celsius at atmospheric pressure. There's an atmospheric pressure at 760. Okay, the bubbles inside equals the atmospheric pressure, right? The pressure inside the bubbles equals atmospheric pressure because it's boiling. That's when the boiling point, let me say that simpler. That's when the boiling point equals, I'm sorry, not the boiling point, the vapor pressure. Beg your pardon. That's when the vapor pressure equals atmospheric pressure. That is the boiling point. At boiling point, okay? All right, so let's do one final learning check. Pause the video, have a look at this, and then come back and see if your explanation is the same as mine. Okay, so let me suppose you paused it. Explain why water boils at a lower temperature in the mountains than it does at sea level. Well, in the mountains, the atmospheric pressure is lower. right? Because you're at a high altitude. And since it's lower, then, and we know that the vapor pressure is equal to the atmospheric pressure at the boiling point. Well, if this goes down, and if the atmospheric pressure goes down and the vapor pressure stays the same, we must have a lower boiling point. All right, hope that's helpful. Let's move on to some more gas laws.